Today, our goal here, we're going to start talking about how to graph a radical function. But first of all, let's talk about why we even discuss radical functions, okay? So let's start with that. Let's do a throwback all the way to the this no the throwback to this, the quadratic, okay? X squared. So the 3 or 4 or 5 easy points that we have learned to do the parent graph are for the x squared. If I go over 2, I go up 1, 2, 3, 4, right? And I go to 1, 2, 3, 4. So I have this right here. So this right here is the standard old basic quadratic function that we all know and love in Algebra 2. Everybody cool with this part? Sweet. Okay, now if I was going to take a look at this function, why do I know, what tests can I quickly apply to show that this actually indeed is a function? The vertical line test. Very good, okay? If this graph passes the vertical line test, that tells me that I have a function on my hands. However, you guys know there's something called the horizontal line test? Oh. And this particular function fails the horizontal line test, right? Because there are 2 points in which my horizontal line touches my graph on a single line, right? Yeah. The horizontal line test would tell you this, right? If it were to pass the horizontal line test, then that would tell you that it would have an inverse. It's also a function. All right? So check this out. If I were to sketch the inverse of this right now, just the way it looks right now, f of x, or y equals x squared, okay? I would do it in blue pen. I'm going to switch all the coordinates of these points, right? The coordinate of this point is -2, 4. So I would have what? 4, -2. Good, I have that point down there. This one is -1, 1. So what do I have? 1, -1. Good. This point is 0, 0, so 0, 0. So this one is 1, 1. Switch it, what would I get? 1, 1. Okay, this one is 2, 4. Switch it, what would I get? 4, 2. Okay, so here we go. I would get this. So ladies and gentlemen, check it out. Because it did not pass the horizontal line test, it ain't going to pass this one either. It's not a function. See that? Okay, so therefore, the inverse is not a function in this one, right? So it does, now, is there something that we could do though? Is there something that we could do that would make our original function pass the horizontal line test? If we restricted the domain, very good. If we restricted the domain to this, here's what he's saying. I love the fact that he's seeing this right away. If I say, okay, if I graph the function y equals x squared for x is greater than or equal to 0, I would have that same black graph, except I would only have these points, wouldn't I? Oh. Right? You guys agree with that so far? Okay, now let's do the same exact trick, and let's switch all of those. Well, I would only have these points. Oh my gosh, that right there is the square root of x. Oh. That's why we study radicals, right? This is the square root of x. It's the inverse of x squared for the restricted domain of x greater than or equal to 0. That's why we're going to be studying these radicals, okay? So it passes the horizontal line test, tells us it has an inverse. The inverse is also a function that makes it a one-to-one function, right? Okay, very good. So now that I have all this information down, we want to be considerate of the fact that when we're graphing the square root function, the points that we're going to have are 0, 0, 1, 1, and what's this one way over here? 4, 2. Those are going to be our 3 anchor points for square root of x. So for families of radical functions, basically we're going to learn how to manipulate these functions. Up, down, left, right, stretch them, reflect them, all that kind of stuff. So the parent function we're going to have, of course, is just going to be square root of x. No big deal. All right. Number 2. If I want to do a reflection in the x-axis, well, then I would have the function, the negative square root of x. So putting a negative sign out in front is going to give us a reflection over the x-axis. Very, very similar to everything that we've been studying before in terms of quadratics, polynomials. Okay, 3. If I want to do a vertical stretch, then I'm going to have an a value that would be greater than 1 for the family y equals a square root of x. So for example, like y equals 5 square roots of x, that's going to be a vertical stretch by a factor of whatever that happens to be. Okay? Stretching is like stretching upwards, like pulling the graph up and down, stretching vertically, right? Now, skinnier upwards, if that makes sense to you. Yeah. We could also have a vertical shrink. I'll do examples to show. We can also have a vertical shrink. What a value would it have to be in order to shrink it vertically? Yeah, 0 less than a less than 1, absolutely, for the exact same one, right? Yeah, some books use the word compression, absolutely. Our book uses the word shrink, but I'm with you on that one. I kind of like the word compression as well, to be honest with you. Yeah. Okay, number 5. We can move things up and we can move things down. How do we move things up or down? Well, it'd be the square root of x plus or minus some value k on the back end, right? So if we add a value of k, it's moving the whole graph up, right? If we subtract the value k, it's moving the whole graph down, just like you would think it would be. And then besides up and down, what are the other two directions we can move something? We can go left and right. So we're going to go left if we have something of this nature. The square root of x plus h. And the h is under the radican. So notice that left is positive h. It works the exact same way that quadratics work because after all they're inverses of each other, right? So they should. So what would right look like? How would I do that? What would it be? You guys got it. It'd be the square root of an x minus an h, and we'd be good to go. Two very simple, straightforward examples. Okay? All right? So what is this function going to do? What is this minus 2 on the end going to do? It's going to go down 2. Notice how I draw the little arrow to indicate which way it's going to move? Well, that's kind of helpful, right? Okay. What about this? What about this plus 3? 3 to the left. There we go. 3 left. Ah, okay. So we're doing really well here. Very, very simple, right? So the first thing we do is we're going to draw the parent graph for each one. There we go. There's the parent graph for each one. This one, this one, and this one. Yep. There we go. That's the square root of x. Square root of x. Square root of x. Okay. For example A, I'm kind of doing two examples simultaneously. If I go down 2, I just move each dot down 2. Very, very simple. Right? Move each dot down 2. And then I could label those points. This point would be 0, -2. This point would be 1, -1. This point would be what, everybody? 4, 0. Very good. Awesome. Okay. If I'm going to go 3 to the left, I'll go ahead and use orange for this one. This dot be going 1, 2, 3 units to the left. This dot 1, 2, 3 to the left, and then this dot 1, 2, 3 to the left. And I would have this, and I could label all of these points. That'd be -3, 0. That'd be -2, 1, and that'd be 1, 2. Right? Look at this one. This one's got 3 things going on here at once, right? All kinds of shenanigans, okay? Yeah, okay, that's good. Let's see here. What is this -1/2 going to do? What's it going to do? Somebody tell me. This is going to be a reflection. And it's going to be a shrink. Okay, hold on, we'll get there, okay? So this is one thing that's going to happen, okay? Tell me what this plus 3 underneath the radican is going to do. This is going to go to the right 3 units. To the right 3 units. And then this piece is going to go up 1 unit. And see how I kind of like draw the arrows to indicate what they do? Kind of fun. Yeah, right? That's called like foreshadowing in English class. Is that right? Anybody take an English class? That's right. They give you some information ahead of time? Alright, anyways. Alright, so no problem. We can do this. So give yourself lots of room here. So I'm going to give myself lots of room. Okay? There's my lots of room. I'll just shrink it down so we can see it all. Okay, lots of room here. Now, when you do this problem, make sure that you're giving yourself a legend here. Sorry. Let's do square root of x first, okay? So the three anchor points that we've got are 0, 0, 1, 1, and 4, 2. You guys cool with this so far? All right. That's our parent function. Very good. Okay, I'm going to change colors so that you know what I'm doing each single time. So the second iteration, I would suggest that we do negative 1/2 the square root of x, okay? Now I'm going to make this graph a little bigger because I need to make a point about what we're doing here. If we are going to reflect it and we're going to shrink the output by a factor of 1/2, all right? So if I reflect this point, well, this one's easy. That would just be there, right? But if I reflect this point, it would be here, but the output is only half as much. So it's really here. See that? If I reflect this point, it would be at -2, but the output is only half as much. So it's there. So now I have this graph. You do it in 2 different steps, but the way I've written it down for you is the negative 1/2 x. I think we're at that point where we can do it all in one. Okay? Okay. What is this -3 gonna do? To the, what does it say? It says to the right 3 units. So take each purple point, bring it over to the right. 1, 2, 3. Take this point. 1, 2, 3. Awesome. Take that point. 1, 2, 3. So now I have this graph going on. This is way more interesting. And then finally, I'll pick a different color like baby blue here. And we'll do the whole entire thing. Negative 1/2 square roots of an x minus 3 plus 1. Yes, the whole entire thing. Every red dot goes up 1 unit, so up 1, and this dot goes up 1. So if I zoom in on this, okay, I would get this graph here. And I could label these points. This point would be what? 3, 1. This is what? 4, 1/2. And this point is? 7, 0, right? Okay. So we'll go back to 100%. And actually shrink it down a little bit. Okay, to check to make sure that we did this right, we're going to take out our calculators and see. Okay? All right. So we're going to enter in exactly the function that was given to us, which was this one up there, so you guys see it again. There it is. Okay. It is negative 1/2 square root of x minus 3 then plus 1. So that's what I have written down here. The negative 1/2 square root of x plus 3 and then, or x minus 3 plus 1. So once it's entered into the calculator, what we could do is we could hit zoom 6, okay, and we would see this right here. But that's kind of hard to tell. It has the general shape, right? But it's kind of hard to tell. So we'll just go to the table, and we would look for what? No, we'd look for these points. Yeah. Is 3, 1 on there? It sure is. Is 4, 1/2 on there? It sure is. And 7, 0. Yep, there it is. So one way to check is to be able to do that. Right, you guys try. You have about 5 minutes or so. I'd like you to show all the transformations, and I'd like you to label your final graph with the 3 anchor points. I have 3 times square root of x plus 2 minus 4. Okay, yeah, so when you're all said and done, right, you should have these 3 anchor points for this quick start right there, okay? Or not quick start, excuse me, you try. That's here. Yeah, there's 7 boxes. So, check this out. How many of you guys know already off the top of your head what the cube root function looks like?
Because you told us about it? Oh, I do remember.
Okay, well, here we go. Let's talk about it. Let's talk about it.
Oh, it's the one where it's like...
It's like 2 horns and then a pitchfork?
What?
It's the snake.
It's the squiggly snake, yes. Okay, so here we go. Here are the anchor points that I'm going to show you, okay? So if I plug in 0, what's the cube root of 0? 0, so that point's on there. What's the cube root of 1? 1, that point's on there. What's the cube root of negative 1? Negative 1, very good. So, does this graph look like this?
No.
No, silly.
I got
Look at what's the next easiest cube root you can think of? Ah, very good. So 1, 2, 3, 4, 5, 6, 7, 8. The cube root of 8 is 2. And then the cube root of negative 8 is also, so 1, 2, 3, 4, 5, 6, 7, 8, negative 2. There we go. So this graph, the parent graph, looks like this. Okay? Yeah. Now, if I didn't, these ones are so far away, this one and that one, they're so far away, I don't make you use them in your anchor points. I only make you use these three because they're close together. But you can see why I don't want you guys drawing this, because obviously that would be in line, all right? That doesn't make any sense. So this is a sideways looking S curve, right? Sideways looking S, kind of, right? And we're going to learn how to graph this one. And all the same families, all the rules that we did right here, all of these rules, they exactly are the same thing for the cube root of x. So all of the rules still apply for the cube root of x. All right, well, that's good news. So for box number 7, for our final box today, we are going to graph this monster function. F of x. Oh, the monster face? There. Is going to be, we're going to graph 2 times the cube root of an x plus 1 and then a minus 4. This is the monster function. Okay? Okay. So, we're not going to plug in the calculator. We're going to do it by hand. We're going to show you one iteration at a time. No, we're going to do it just like this. Okay? Alright, here we go. Alright. Alright, let's talk about what each thing's going to do. Alright? First of all, what is this 2 going to do? It's going to vertical stretch by a factor of 2. So vertically stretch.
How do you stretch a squiggly line?
I'm going to show you. By a factor of 2. Okay? What is this plus 1 going to do?
To the left.
1 unit to the left.
Down 4.
And then finally down 4 units. Alright? Everybody understand the game plan so far? Alright, good. So what do we start with? We start with the parent function, which is the cubed root of x. Alright? So I have 0, 0 as an anchor point. I've got 1, 1. I've got negative 1, 1. And I would have a sketch that looks like this. That's what I expect as the sketch. You only need 3 anchor points for this one, but you have to know the general shape of the cube root function. Okay, and the next one that I suggest that we do is we do 2 times the cube root of x. So we are multiplying the outputs by a factor of 2. Okay, so instead of, well, 0, 0, that's pretty easy, right? Instead of 1, 1, I'm going to have 1, 2. Very good. And instead of negative 1, negative 1, I'm going to have negative 1, negative 2. So the entire graph has been stretched vertically by a factor of 2. Every single point. And again, we're using these 3 anchor points as a sketch for our function, for our problem here. Okay? I'll go to orange now. And then I'm going to graph y equals 2 times the cube root of an x plus 1. Alright, so what's that going to do? 1 to the left. You got it. 1 to the left, 1 to the left, 1 to the left. And it would look very, very similar to my pink one, except this is moved 1 to the left. But very, very similar in shape. And then lastly, I will do that in purple for you. We're going to do y is 2 times the cube root of x plus 1, then a minus 4. So each dot, 1, 2, 3, 4. 1, 2, 3, 4. Good. Finally, 1, 2, 3, 4. So my graph would look like this. Right? Kind of funky. And to be conservative of your time, I've already plugged this one in, and it would look a lot like what we just came up with, this graph right here. Check out that the line there, right there. Okay?